Hello, hello. Are we live? Looks like I'm live. All right. So I haven't really done any cool demos of my language Syntran yet. I've mostly done like short one-line tests and maybe up to like 3 or 4 line tests on these streams. So I'd like to write something a little bit more in depth to show off uh, the the language on like a larger example. And to do that, I'm going to calculate pi. And then once we have pi, I think I'm also going to try to calculate a sine function, not using any intrinsic, like not using anything built into Fortran or built into anything else, but like implementing my own sine function. So this is what we did last time. Let me clear this out. So I have to get my Callie. Don't cry, Callie. It's okay. I'm just streaming. Good girl. All right. So yeah, this is what we did last time. Let me clear this out and start something new. Twitch 6. All right, so we're going to calculate pi. And to do that, I'll wrap it up into a function. So function, it's not going to take any arguments. It's basically going to return a constant. So it doesn't need any arguments. And it's going to return a float 32. I don't have float 64s in the language yet. As this is a toy language, I just want to have like one integer type and one float type. I'm not really planning to add a bunch of floats anytime soon, like float 32 and float 64, or even float 128, which I think some languages on some hardware support float 128. But I don't have any immediate plans for any of that. And for now, we're just going to say, just to test that I declared the function correctly, pi is exactly 3. Let's check that I can do that. And then outside of the function, we're going to call it. You could put this inside of like an explicit main function, but I'm just going to put it in the global scope here. So let pi equals get pi. And let's print it explicitly, even though this will kind of get printed automatically. Run that, but run the new program that we just wrote. Wrong types. Oh. Yeah, there we go. Okay, so now what I actually want to do is I want to initialize it to 0, because obviously pi is not exactly 3. So start it out at 0, and then I'm going to use an infinite series representation of pi, which I have to look up because I can't remember it. And Wolfram Alpha has a bunch of these. Come on, Google Chrome. So Wolfram pi formulas. We should be able to find it here. And I've looked at this list before, so I know which one I want. I think is it, yeah, BBP? Yeah, it's a BBP formula, whatever that stands for. Bailey-Borwein-Plouffe. Okay, this is a Bailey-Borwein-Plouffe formula. And then a lot of these expressions are pretty long, so like if I typed this, that would be quite a few lines of code or quite a few expressions. But this one, line 41, or equation 41, that's fairly compact. It doesn't have a whole lot of terms. It's an infinite sum. Basically, all of these are infinite sums because pi is an irrational number. So you can't represent it with any finite sum of rational numbers. So it's an infinite sum and then there's this 1 over 16 to the k term, and then we just have 4 terms inside of the brackets, and all of them are just relatively simple expressions, a numerator and a denominator, where the denominator depends on k. So this shouldn't be too bad to implement. So yeah, the reason I initialized pi to 0 here is because this is an infinite sum. So we want to start pi as 0 and then add each term, but we want to start with 0 because that's how an infinite sum is defined. So the first term is there, well, before we get to the first term, we need a loop. So we need for k in, obviously we don't want this to be literally infinite because then it would take forever to compute, but we want to get an approximation of pi. So the thing that you can see is there's this 1 over 16 to the k term. As k gets very large, this 1 over 16 to the k term will get very small. So as you get to higher and higher values of k, this will approach 0, and that means that we can get a pretty good approximation of pi by just summing a few terms, and it should converge pretty quickly. So I think I only need to do about 10 terms. Yeah, so we'll do for k in 0 through 10. That will actually go from 0 to 9 because it's not inclusive of the upper loop bound. And then we're going to fill in the body of the loop here. I just want to make sure that that still compiles. Yeah, pi is 10. Okay, I actually didn't know what Cintran did here. If you have an empty loop at the end of a function, the function will return the upper bound of the loop. And I guess that kind of makes sense. It only gets to 9, but it returns 10, so that's kind of interesting. Anyway, that's not the point of this demo. So inside of this loop, we're going to add up pi. So pi plus equals, we can use this cool plus equals compound assignment operator, or one of the compound assignment operators that we spent several streams working on. Callie, what's up? Yeah, we need to do 1 over 16 within the loop. So 1 over 16.0, I need this to be a float. Callie. My cat's going nuts in the other room. Callie, what are you doing? What's wrong? What's out the window? Are there birds out there? Yeah, so 1 over 16, and then we have all of these terms with the numerators and denominators. So that's going to be times, let's indent it like this. This is sort of a long formula, so I want to break it up into multiple lines. What was the first one? It's like 4 over. Let me zoom in too. Yeah, so the first term is 4 over 8k plus 1. Some of these need to be floats. So which ones need to be floats? Is it plus or minus? I think it's minus the next term. It's minus 2 over 8k plus 4. And then I think the rest of them are all minuses. 1 over 8k plus 5. I think there's one more, 1 over 8k plus 6. Assuming I haven't made any typos, and I probably have made some typos, I think that's it for the basic body of this function, and then I need to return the right value. So Cintran doesn't have an explicit return statement. At least it doesn't have that yet. Kelly, she's mad that I'm streaming instead of giving attention to her. So if I haven't made any typos, this might be it. Let's see if that compiles. Yeah, would you look at that? It's basically correct up until the last decimal place, 3.14159. It is correct on the last decimal place because it's 26. 3.1415926 would be the next two places. So instead of 2, I have a 3, but that should round to 3 anyway. You can see if I only do one term, this isn't going to be very accurate. Even just one term, that's fairly close. It's 3.13 instead of 3.14. If we do a second term, it gets even closer. The cool thing about this formula is that it converges very quickly. So even after just 2 terms, we're up to 3.141, and then almost the 4th decimal place. The 4th decimal place is almost correct. So as we keep adding more and more terms, this gets closer and closer, and it converges pretty quickly. So you don't need anywhere near infinite terms. Just 10 terms gets you about as close as float 32 can get. So float 32 basically just has 6 or 7 or 8 decimal places. So float 32 can't get any more accurate than this. If we had float 64, we could get up to about 15 decimal places. And we could probably use the same formula. But for float 32, this definitely works. So that is pi. What is up? Okay. I thought I had trailing white space there, but I don't. Yeah, so that's pi. Next, let's try to calculate a sine function. And for that, pi is going to need to be a global variable. So I'm going to put it below here. I'm going to call it my sine because you shouldn't use this in production. You really shouldn't use any of these in production. Eventually, I will probably add intrinsic functions for these things for Syntran so that you can get pi and you can calculate trig functions without implementing it yourself. And for those, I probably will fall back on the built-in Fortran intrinsics. That way they'll be fast and accurate, and I don't really have to worry about it too much. So sine is going to take an argument. Getting pi, you don't have any arguments for that, but sine will require arguments. So it's going to have x float 32, and it's going to return float 32. And again, we're going to do an infinite series, so we'll start it out with 0. And then, as an example, sine of 0 is 0. Sine of, I guess we don't really need pi inside of the sine. I just want to have pi so that I can calculate angles in radians. So I'll move this below the sine function. And then sine of 30 degrees is 1/2. So I want my angle to be 30 degrees, but 30 degrees in radians is pi over 6. Know why I'm spacing things like that. And then let's print that. What the hell am I doing? Don't know how I got that extra parenthesis in there. Okay, so obviously it's not 0 because we haven't implemented this function yet. For this, I'm going to use the Taylor series of sine. Clicked the wrong window. Okay, Google Chrome, that's what I want. Sine Taylor series. I think we can find this somewhere. Maybe we'll have to go to the MIT website. Okay, there we go. Okay, so this is an interesting one. We'll need factorial, but I don't want to make a factorial function. I just want to do this in line within my sine function. So it starts at x, and then we basically only have odd powers. So we have x to some power divided by some factorial expression. And the sign also changes. So we need a sign, like sign for plus or minus. We need x to some power, and we need a factorial. And then we need to do those only for odd powers. So let's do it like this. Come on, window switcher. There we go, that's what I wanted. X to some power is going to start off at x. Sine is going to start off at positive 0. I think this one can be an integer. And then factorial is also going to start off at 1. I want this to be a float, because factorials could quickly overflow for large integers. So I actually want to do factorial as a float. Yeah, so at the first term, those are all 1. And then at the second term, because these are odd powers, we want to go to factorial of 3 and x to the third power and negative 1. So again, just like the pi function where we have a loop, we're going to use a loop for the sine function as well. So for k in, let's start off with 0 to 10 again. We can make this bigger or smaller depending on how much we need this to converge. So we're going to do s plus equals, we can use plus equals again. This is the sine result of the function. So it's going to be x pal sine times x pal divided by factorial, right? If you look at every one of these terms, there's a sign, it's a plus or minus, times x to some power divided by the factorial. And so that's what I've coded up here, and then we just need to update the sign and the power and the factorial for each loop term. And how do I want to do that? Because I have to be careful. I have to be careful that I start at 1 and I only do odd powers. So, I also want to calculate x2 and have that cached so that I don't have to, or x squared so that I don't have to recalculate it every time. X to the 2. Syntran isn't optimizing, so it might actually be more efficient to do let x2 equals x times x instead of x squared with the built-in exponentiation operator, but I just want to show that this exponentiation works. So at every loop iteration, we start at x, and at the next loop iteration, we need to get to x cubed. So to get from x to x cubed, we have to multiply x by x squared. So x is going to be times equal, x pal is times equaled x squared. right? Because this starts at x, and then if we multiply it by x squared, we'll get x cubed at the next iteration of the loop. And finally, we need the factorial. So factorial is a little bit tricky because I'm looping through every integer k, but I only want to end up with the odd factorial terms. Like I want 1 factorial, 3 factorial, 5 factorial, and 7 factorial, but I want to skip the factorials for the even numbers. I keep clicking on the wrong window and messing up my window management. Okay, so here we go. Oh, the easy thing is the sign. The sign just becomes the negative of whatever it was. There is no compound assignment operator. I could do sign times equals -1. Yeah, actually I like that. So that way I can use the compound assignment operator instead of writing out SIGN on both sides of an assignment operator. That's what I've spent the last few streams doing, so I want to use this demo to show off the features that I've been working on. Yeah, so the factorial is going to be times equals, I don't think I need parentheses. So at the first iteration, you want to multiply by 2 and 3. So that's going to be k plus 1 times 2. I think I can make this easier on myself and start the loop at 1. That way the factorial expression isn't going to have a bunch of off by 1 terms. So I need to multiply by 2 and 3. It's going to be 2k and 2k plus 1. So I'm only thinking about the first iteration. I'm not worried about k equals 2 or k equals 3. So at k equals 1, I want 2 and 3. So that's 2 times 1 and 2 times 1 plus 1. So 2 times k and 2 times k plus 1. I think that might be it. If I could resize my webcam by just 1 character, this would be perfect. Okay, there, now you can literally see my entire program and nothing is in the way. Perfect. All right. Yeah, assuming I haven't made any typos, I think that sine calculation should be correct. And the thing that we're expecting is sine of, that's 30 degrees. Sine of 30 degrees should be 1/2. So we're expecting this to print out pi and then print out 1/2, if I've done sine correctly. No, that's way off. Okay, so what is wrong? Let me add some parentheses. Let me get rid of this print. Oh, I'm not returning anything. Is that all I did? That was it? Let's try to get rid of these parentheses. Yeah, that's it. There you have a sine function. The thing that I forgot is just to return s. Otherwise, it was returning the factorial because that was the final statement. Was it returning the factorial or returning k? It must have been the factorial. Was it like 1 to the 17? What's 10 factorial? Let's use Python to confirm. Is Python going here? Oh. I think we have to do our own factorial. Yeah, let me just use Wolfram. Yeah. Okay. So that didn't work. So what the hell was that thing that we were calculating? No, it's not even close to 10 to the 17. Oh, but it wouldn't be 10 to the 17. It would be like the 10th odd term. So would that be like 19 or 21? Yeah, is that what it was? 1.21 times 10 to the 17? Yeah, 1.21. So that was 19 factorial that we were returning when we didn't have this line. When we didn't have this line. Yeah, 19 factorial. But if we return the right value instead of this line, so if this line isn't here, then this is the thing that the whole sine function returns. But with that correct return value, it's exactly what we expect. We can check some other sine values. Yeah, let's do a loop. So for I in 0 through 12, let's do 0 through 13 to get the complete cycle, and we're gonna go in 30-degree increments around the entire circle. So the angle is going to be I times pi over 6. And then the sine function is going to be the sine of whatever angle that is. So we're going to print the sine of, it's no longer sine in degrees, it's just sine in radians. Sine of x equals sx. I think that's basically what I want to demo here. What else is getting printed? I think is this return value? Okay. Yeah, I have this quirk in Syntran where if you just have an expression, like just one variable identifier, this gets printed. I probably want to make the language not do that so that I can return things from a function without suppressing the print like that. But for now, now it only prints these things. If I had this instead, if I comment out the rest of that line, it's printing the sine value there, and then it prints the sine value again right there. But that's a little bit noisy. So I'll just suppress the printing like that. So yeah, sine of 0 is 0, sine of 30 degrees is 1/2, sine of 60 degrees is, what is this, like the square root of 3 over 2? We can actually use Python for that one. Square root is not defined. Okay, there's the square root. Square root of 3 over 2, yeah, 0.866. So the sine of 60 degrees is 0.866, and we just confirmed that expected value here in Python. And then what else is it printing? Let me get out Python. Let me rerun that so I don't have to scroll up. Yeah, sine of 90 degrees is 1 up to rounding errors. So it's not 1/2 exactly. These are just floating point rounding errors, so you almost never get exactly the value that you expect. And then after this, we basically get repetitions of previous sine values, sometimes with a plus or minus sign difference. So again, it's the square root of 3 over 2, 1/2, basically 0, negative 1/2, negative square root of 3 over 2, negative 1, and so on. And up to here, the Taylor series stops converging. So Taylor series only, this is using a Taylor series expansion around x equals 0. Yeah, that's good enough. So Taylor series only converge close to the point that you expand them for. So as x gets further away from 0, this doesn't converge as well. It might help if we use more terms, if I go up to 20 terms instead of 10. Let's see if that helps these last couple values. And then this one should be basically 0. It helped a little bit. Yeah, this term is a lot better, and now we have like 10 to the minus 6, which is about as close to 0 as we can get with float 32s. Yeah, and again, don't use this in production. It's slow, and like we're seeing here, it's inaccurate for large x because the Taylor series only converges near x equals 0. Eventually, I'll have intrinsic functions for all of these things. I already have intrinsic functions in Syntran for x, the natural exponential function. Callie, what's up? How you doing? You trying to lick my hair? You trying to take a nap? You trying to drink my coffee? Yeah, so wait until I have these intrinsically in Syntran. Let me try to calculate a decent line wrapping. What column am I at? Kelly, I can't see anything. If I do like a line width of 50, that should be okay looking. It's really hard to see around Kelly. So let me set my text width to 50 and then wrap those. Okay, now the comments don't look ridiculous. I think I can probably do 56. That's a better number. Yeah, and it still looks okay. What's up, Kelly? She's like right here on my mouse pad, just outside of the camera's range. Some chin scratches. Good girl. I also have my French press sitting on my desk, and she's right next to that. The plan was that I can refill my coffee without taking a break. But now it's sort of dangerous because Callie might knock over my half-full French press of coffee on my desk. Yeah, so the point that I was getting at is don't use code like this in production. The point of this is to make a demo. I can get to my mouse. Callie's like right in front of my mouse. So the point of this demo is to show off like exponential operations, compound assignment, like we have plus equals and times equals. Not using minus equals or divide equals. I went ahead and implemented divide equals off screen yesterday. But I think in most code that you write, you're going to end up using plus equals and times equals more frequently than any other compound assignment operator. So those ones are implemented, but don't use this code in production. Wait until I have intrinsic functions, like if I can show you some of the existing intrinsic functions. I have exp intrinsically right now, so let x equals exp of 1.0. This should be e or like 2.7, whatever. There we have it. So that's the natural exponential function. This is intrinsically in Syntran. You don't have to implement it yourself like I just did for sine. And then we can do other values like exp of 2. I don't know, that's going to be like 9-ish, 8 or 9-ish. Yeah, I can't do math in my head. I don't know what exp of 2 is. I only know exp of 1. But sine does not exist. So if I try to do sine of it, undefined function, I define it over here, but this is the interpreter, so it doesn't have access to this thing that I just implemented in some random Syntran file. So yeah, it's not defined. Yeah, I think that's it for the demo. I'd like to put this in a test. Actually, I have a similar test existing to this, but I didn't use compound assignment operators. So I've done this before off stream. That's how I knew to get to this Wolfram formula. I had browsed this article a little bit more thoroughly, and I narrowed it on this one. It looks like it should converge fairly fast, and it looks like it's not too hard to implement. Like we did this in 15 or 16 lines of code. And it's only 16 lines of code because I broke this expression into multiple lines. If you did this all on one line, it's the same number of characters. So lines of code is a bad metric. But the point is this isn't a super long function and it gets pi pretty accurately. Yeah, so now that I have this, I would like to make a test for this because I've done this before, but without the compound assignment operators. So like these expressions were a little bit more expanded. Yeah, and the point of this is to return without printing. But it's a hack. I should fix this in Syntran. I have mixed feelings. I want to have easy ways to print. I used to not have print line. So now that I have print line, I should take out this holy C method of printing, where if you just do S automatically gets printed. That's kind of like the way that holy C works in Terry Davis's language, where if you just type a string, it prints the string automatically. And then I went ahead and did that not just for strings, but also for integers and any type. But now that I have a print line intrinsic function, I should take that out of my language because it's kind of annoying in situations like function returns. So let me double check that that still works. That's not what I wanted to run. I wanted to run the Syntran source file. Yeah, that still looks about right. I want to print this. Basically, I want to test everything in this table. I don't just want the test to be one sign value. I want it to be everything. So we can make this a little bit more testable. First of all, I want to copy this out of my Scratch directory. So I already have a collection of Syntran test source files, and they're all under here, organized into subdirectories. And I think I have the similar ones under F32. We have a bunch of things in here. We also have functions and loops. But I think the first time I did this, it was to test F32. So let me see what one of those files is. I think this is one of the sign implementations. Yeah, so this is a sign implementation, and this might have compound plus equals. Yeah, this has plus equals, but it doesn't have times equals. So I was doing like the factorials and the sign a little bit in a little bit more verbose way. So I want to copy this into that same directory, but I don't want to overwrite that test. And then I want to edit it over here so that I can verify the outputs of these functions. Should be 4. Yeah, this is the one that we just wrote. Yeah, this is test 04. So I want an array. Let me parameterize n. So n is going to be 13. So this still runs, it still does all 13 things. And then I want to save these into this array that I just made. So instead of printing this, I want to push them into the array. So sign array I equals sx. You could do this without the temporary variable. Actually, it might be good to test this without the variable. And then I want to print the whole array just to verify that I've saved everything correctly. I know that's behind the webcam, so there you go. There's the entire array. Now I want to compare this to the expected value. I just looked at all of these values individually, so I'm confident that these are as close as they should be. So what I'm going to do for the test result is to just copy and paste what I have right here, because I'm confident that these are correct. Like we verified 0, 1/2, square root of 3 over 2, 1, up to some rounding error. So again, there's a little bit of rounding error. What we're going to do for that is add all of these up and compare them to the expected values, and then subtract it from some small numerical tolerance, so that even if you test this on different hardware where like the floating point results come out slightly differently, the test will still pass. So let me zoom in on this pane, and then now I can copy and paste, zoom out, and we're going to make a new array for the expected values. So expected, just have to type it out, can't tab complete anything. Paste. Okay, these are line wrapped, but that's fine. Then it prints the sign array and it prints the expected values too. And then I just have to compare them. So we're going to compare them, and then we're going to add up a norm of the differences. I'll use the 2 norm. So let norm equal 0, and then so n, we already have n, but maybe I want to go through the size of expected instead of n. Has to be 1. So Syntran has this intrinsic function called size. It will tell you the size of an array along a certain dimension. So expected is a vector. That means it only has one dimension. So the size of the first dimension is just 13. We actually don't need brackets. If you have a for loop with only one line inside the body, then you don't need brackets. It's just like C. So norm plus equals, it's going to be a sign array minus the expected value, and we're going to square it because this is the 2 norm. And then let's see what that is. No. What's wrong with that? That's weird. Is it? Oh, it's 0. Yeah, I forgot how my zero-based indexing works. I think I want to print something in here just to be sure that I'm adding up the norm. So it starts at 0 and then we add up the differences. There are some rounding errors because I'm only printing 6 significant figures. There are more decimal places, but they don't really matter too much. So even though I copied and pasted the expected values exactly, I didn't copy and paste them exactly because there are only 6 decimal places. So some of these norms are not 0, and we end up with a non-zero difference. And then I don't know if this whole program should return the norm or if it should just return a Boolean value. I think I want to return a Boolean value. That way my tolerance is in here, and I don't have the calling testing program. The calling program won't have to worry about the tolerance. So I just want to make sure norm is less than tall. Let's do the absolute value just to be double sure, even though the 2 norm should always be positive because we squared everything before adding it up. The difference of the actual sign functions to the expected sign values, that difference should be less than this small tolerance. And then the final return value of this thing should be true. That didn't work. Oh, I don't have abs. Yeah, undefined function abs. That's an intrinsic that I need. Do I have that in my to-do notes? Yeah, that's in my to-do notes. So I want... That's the way that I have to do absolute value for now. Instead of just one thing, I have to compare 2 things with a minus sign. And now that's true. We can delete some of these things. Wait, that's not what I wanted to delete. And I also want to remove the rest of the prints. Do I? I'm not sure that I do want to remove all of the prints. I think I can leave those in there, and then the calling testing function will set a quiet flag so that this doesn't print anything. But then for debugging purposes, we can run this manually, like with this, like this. there are different ways that you can run it. You can type out the path to the Syntran interpreter and then do this. So that's another way to run the exact same thing. But yeah, if we run it like this, it still prints, and this is helpful for debugging in case this test starts failing in the future if I break anything. But for now, that should work. Just pouring a little coffee. All right, so let's actually test this. If I run my testing script, we get 429 tests right now, so if we add this, we should get up to 430. And where do I test these? I think it's F32.2. Yeah, these are scripts. Every one of these tests interprets a whole Syntran file, and then we just added number 4. So we can copy and paste that and make that 4. And they all output a Boolean. So like we just saw in this window, it should print out true at the end. So that final value should be 2. We verify that in the test. This should be 430 now. And there it is. Oh, it is still printing, so I do want to comment these out. Unless, yeah, I'm telling it to be quiet, but when I have explicit print lines, it doesn't make those quiet. So I just want to comment out all of these. And now that should test quietly. Because like I don't want to see this in the test output. Yeah, there we go. 430 tests passed and nothing polluting the test logging. I think I want to commit that as a test. That's an untracked file. I think I made some notes to myself in core, so I don't want to actually commit that. Yeah, I just made a comment. Yeah, and I don't want to commit that yet because I want to do that next. But I do want to commit this, and I want to commit this new file which we just made on the right. So git add. I don't know if you saw that, but there's this cool thing about git add, where if you use tab completion, it will only tab complete to things which are untracked. So instead of tab completing to test 0.1, once I got up to this point, I hit tab and it jumped all the way to test 0.4 because that was the only untracked file in this directory. So I have no idea how git does that, but it's very cool. And then I want to add this thing too. And then I just want to commit -m instead of commit -am. And that's it. So next I think I want to do a little refactoring. Check that pushed first of all. There it goes. It's going to run on the cloud. So I think I want to do a little refactoring. That demo took a little bit longer than I expected. I was thinking about maybe adding some more features today on the stream, But I have a lot of technical debt from yesterday with some things that I want to clean up and refactor a little bit more. So I think I'm going to just do that. And like I showed in the diff, I already have a note to myself there. I also need to add more tests for the slash equals. I did add compound division assignment yesterday, so I need tests for that. I think I want to do that first and then refactor. Like if we look at all of the plus equals, copy and paste these and then test divide equals as well. It's going to be a little bit boring to do this on stream here, but nobody's watching, so who cares? So I'm replacing all of the plus equals. Well, first of all, I copied and pasted, and then I'm replacing all of the things that I pasted with divide equals. I want to leave this last one the same because there's no comma here at the last thing in the array. So I like to leave this one here so that I don't have to worry about the final trailing comma or not. And now I want to make the math correct. Let's do 12 divided by 3 should be 4. Half divided by a quarter should be 2. Let's start out with just testing a couple. And comment out the rest of those for now. So now we should have like 432 tests, I think. Yeah, we should have 432. All right, let's work on the rest of these. There are no strings. You can't divide equals a string. So just delete those ones. That one is correct now. Why do I have 2 of these? Oh, it's the explicit return, or just having this as the final statement. So that's why it's not the exact same thing twice. There are subtle variations. It's not super important that I change these numbers. 10 divided by 5 should be 2. So then we should have 2, 10, 10. 10 divided by 5.1, that would only be 1. Let's make this 4.9. And then that should divide to 2. Actually, it's going to be 10 divided by a float, so it's going to be 2 point something. But then when that gets casted back to an integer, it should be 2. I'm a little bit lazy and like just reusing the same numbers for all of the tests. Yesterday, one of my viewers recommended that I write some fuzz testing. That's a great idea. I should fuzz test expressions like this, but with random numbers, and then check those results. But I'm not doing that just yet. What I'm going to do here, maybe 4.9 again. Then that should be like 4 when we cast it to an integer. This one... should be 4.1 if I've done the math correctly. So let's see how many of those I messed up, because there's a very low chance that I did all of that correctly. Okay, test 54 failed. So if I jump to the top and then do 54 down, I believe that means this test failed. So just to double check that that's the one that failed. Yeah, everything passes with that. So 10 divided by 5, there's going to be some floating point error. It's really dangerous to do these with floats. Is 2 not a machine number? It's exactly that. Oh, it's the exponent. It's 2 times 10 to the 0, not 2 times 10 to the 1. I was worried there was rounding error, but there isn't. It's user error. That's on me. That's not what I wanted to run. There we go. That one passes now. And again, I think it's the same thing for a couple of these other ones. So is that all? Yeah, it looks like those are all passing now. So I think I can commit that. Delete that to-do note, because that is done now. That is done. Like the only compound assignment operators left are modulo equals and then logical operations. So I'm not going to do those yet. But I think I can commit this. I implemented this feature quickly off screen yesterday, but I didn't write any tests, so it's very critical that I add tests for that now. I want to verify that those actually passed, so I'm going to wait a minute and let this run. Yeah, debug passed, and this is release now. It's a difference of whether the interpreter itself is compiled with debug flags or release flags, so it basically does these twice. Yeah, and that passed too. I don't need to wait around on Mac or Windows. Those take a little bit longer to run, which is weird because Ubuntu actually has to install G-Fortran for Scratch every time. Oh, 0 newly installed. G-Fortran is already... I think there's a bug here where if you don't try to reinstall it, then the Ubuntu cloud thing that's running in GitHub Actions can't actually find G-Fortran. Or at least that used to be the case, so I had to add this step where it installs G-Fortran from scratch. Mac has to... yeah, with Mac I installed GCC. Then Windows doesn't actually run anything because there's some kind of bug on the GitHub cloud where it can't run GCC executables on Windows. But it does compile on Windows and verify that that passes at least. So I think I feel good about that. And then the next thing is refactoring. So basically every time I add a compound assignment operator, I have to add it here for scalars, and then I have to add it again for array elements. But as I've gone through several iterations of refactoring this, I've realized that they're the same, and that I don't have to do it in two places. I can make it a function and dry this up a little bit. So that's a little bit of technical debt that I want to address right now. So it's here for arrays, and I think right above it, it's here for scalars. I should be able to make this a function. We have equals, we have regular assignment, and then we have all of the compound assignment cases. And then here, it's the exact same thing. We have equals, and then we have all of the compound assignment cases. So I want to make a function for that and basically call it like this. So for arrays, it was a little bit different where we had this get array value, and I used to have this inside of each one of the cases, but then I refactored it out and deleted a bunch of redundant lines of code. So now it's more obvious that the array element case is exactly the same as the scalar case. So I can dry this up and delete a bunch of code right now. I just have to turn it into a function. Do these set the type? I think these don't set the type. I think this needs to be a subroutine and not a function. So like if I go to add res, yeah, the type is set before calling this routine. So this is an in-out argument, and that means it has to be a subroutine, not a function. So I can't call it like this. This is specifically for compound assignment. This is not for binary expressions. So I don't need to pass this argument twice for like the left-hand side and the right-hand side. I only need to pass it once because that's the way that compound assignment works. So I think we can do that. And then we're going to cut this out and make it a function. And where is my next subroutine? I'm going to put the function right here. Or, yeah, right here. It's a subroutine, not a function, but sometimes I say subroutine when I mean function or vice versa because they're nearly the exact same thing in Fortran. Fix the indentation. End it. It's not subtract, it's subroutine. Tab completion gets me like that sometimes. I don't type enough characters and then I tab complete to the wrong thing. What are these types? They're going to be kind of like these. So I'm just going to copy and paste this and then modify it as needed. It's not an array val though, it's just a val. This one is intent in-out because it's like on the left-hand side and the right-hand side. I don't want to call it array val. I want to rename this locally. Yeah, let me search like that, and then replace that with LHS dot. I need to use the dot command more frequently in Vim, which dot just repeats the last thing that you did, and that is replace this word with LHS. So that's a little bit easier than typing out the regex for, or like the search replace regex for this thing. And that's it. So I can jump back here, scroll up a little bit. Yeah, so this is LHS, and then I want another one, but it's intent in for the right-hand side. You get the idea. So that's what this subroutine does, depending on the operator. So I don't want to call it node op locally within the function. I just want to call it op, and that's going to be a token. If I can remember the way that I've named my type, it's been a while since I wrote one of these. I could just look at one of my other functions, but let's try to do it like this. And there's no I. I need to search for node, and then I can use the dot command again here, so I want to delete two words, D2W. Yeah. Oh man. That's the way that you're supposed to use Vim. I think I don't need a line break here anymore since I've cleaned up. Yeah, I got rid of a couple indentation levels, and now I can do this on one line comfortably with plenty of width to spare. So will that work? Where am I calling this thing? No, of course it doesn't work. Oh. This is RHS. And then I forgot to search and replace it. I think that should compile now. Let's see. It's thinking. It did it. Hey, all the tests passed. So can I go ahead and replace the other one now? Yeah, this is so simple now. This is so nice and clean. And now I can use this up here as well. But instead of, I just have to change the names. So it's going to be this thing. I don't know how I copied that. Nope, that's not right. Yank that. There we go. So, is that what I need to do? Hopefully everything still passes. All right, that went pretty smoothly. I guess I might be done for today. Yeah, I think I'm basically going to commit this, and then I'm done for today. That note isn't really relevant anymore. Maybe I should rename this. So the first case is just regular assignment. So this isn't necessarily compound assignment. I think that's basically it. So let me verify that that pushed. Yeah, I think that's it for today. So thanks for anybody who tuned in, and I'll catch you next time. Bye.